Hi, welcome to Phi Mathematics, our cafe calculations. We are here in beautiful Seattle at the wharf here by Pike's Place. Cafe calculations is where we try and make math a little more accessible to people, a little more interesting by presenting it in a more relaxed setting. And I've always found the best way to do math is over a cup of coffee or whatever favorite beverage you have, and just sit down and enjoy the process. If you like our content, please like, comment, and subscribe. And don't forget to turn on those notifications so you'll know every time I have a new upload. And to become a patron for exclusive content only, please see the description box below. Today's cafe calculation is going to be integrating the Gaussian curve. And the Gaussian curve is e to the negative x squared over all space. So curve, if you know, kind of looks like that over all space. And it's a little more advanced lesson, but it is a very interesting one, and it uses some nice techniques in mathematics that we tend to forget. So let us begin. So first we're going to start with the integral over all space from negative infinity to infinity. I'm going to let I equal this whole thing right here. Then I'm going to rewrite it as I equals integral over all space, e to the minus x squared dx. Now if you do this traditionally by integration of parts, you will find that you can't represent it properly and you get stuck. So there's a simple technique in doing this. I'm going to square this, so now I have an I squared. So I'm going to rewrite the same integral I have here, but I'm going to use a dummy index. I'm going to pick a y as opposed to the x. Minus y squared over dy. So it's the same thing, just over a different variable. Now, I can use my integration rules and my exponent properties to smush this thing down to the following. I squared is equal to now a double integral, once again over all space for both of these guys. E, now I'm going to simplify it to the minus x squared plus y squared dx dy. So by squaring it, I've ended up now with a double integral over x and y. And the reason for that is the following. Now here's the trick in solving this integral. You got to translate it to a different set of coordinates. And this is a typical technique we use all the time in mathematics. If you get stuck in one area, transfer to a different area where it's a little more easier on the math. So in this case, we're going to translate over to polar coordinates. And that goes as following. If you remember your polar coordinates transformations, it is x is equal to r cosine theta, and y is equal to r sine theta, with our dx dy equaling r dr d theta. Okay, so let's push all these substitutions into our integrals and see what happens. So we're going to put our two integrals. I'm going to leave the limits of integration alone for just a moment. I'm left with e to the minus, parentheses, x squared is this right here. I get r squared cosine squared theta plus r squared sine squared theta, close parentheses. Substituting dx dy to this over here, we get r dr d theta. Now the reason for this is, first thing I'm going to do is I'm going to factor out this r squared in this exponent, and you'll see what happens. And I'll come back to the limits integration in just a moment. Okay, so we're left with e to the minus r squared, we factor out, cosine squared theta plus sine squared theta, close parentheses, r dr d theta. Now let's go to our limits of integration. In polar coordinates, r can extend out all the way to infinity. So the limits on the r index is still 0 to infinity. But in polar coordinates, the theta is over 2 pi. So it's just from 0 to 2 pi now. Now we can attack our integral. Polar is the following. Cosine squared plus sine squared from our Pythagorean identities, we know goes 1. That simplifies the integral amazingly. Therefore, we end up with 0 to 2 pi, integral 0 to infinity, e to the minus r squared r dr d theta as theta. All of a sudden our integral is looking much more easy to attack. We're going to deal with just the inside integral, which is over r first. So I'm going to just write this one. So I get 0 to infinity of e to the minus r squared r dr. This is going to be a straight substitution method, so I'm going to let u equal r squared, therefore du equals 2r dr. And as you notice, we have r dr, so if I rewrite this as du over 2 equals r dr, now I can make my substitution directly, and I'm left with 0 to infinity of e to the minus u du over 2. As you see, this is a much easier integral to solve. This translates down to then integral of e to the minus u is minus e to the minus u all over 2, and we're going to evaluate it from 0 to infinity. If we do that, we're left with minus of, we'll bring out our half here, actually make life a little easier for us. We're left with then 1 over e to the infinity, when I bring it back down because of the negative exponent, minus 1 over e to the 0, close parentheses. Well, 1 over e to the infinity goes to 0, and 1 over e to 0 goes to 1. So negative 1 times negative a half is just equal to a positive half. So this integral over r goes down to 1/2. We just now do the theta integral and we're done. Integral of 0 to 2 pi of 1/2 d theta, and this is still equaling I squared. Well, integral over theta is just going to be theta. Let's put this, we'll put this over here a little bit. So we're left with 1/2 of theta evaluated at 2 pi and 0. Well, this becomes 1/2 2 pi minus 0. Well, 1/2 times 2 pi is equal pi. Now I'm just going to draw this over here, so remember, let's recall though that this whole thing was I squared is equaling pi. Therefore, the result we want is really I. We take the square root of both sides. We really just want the I. So I is equal to the root pi. And therefore, the integral of over all space of e to the minus x squared dx is equal to root pi. This is actually amazing to get such a clean integral for something over all space as something as the Gaussian function. Thank you very much for joining us in our cafe calculations, where we try and make math a little bit more pleasant and reflect the art side of mathematics. I want to remind you that there will be a supplement fine mathematics lesson on this, which goes much more slowly, and I encourage everybody to go through this because it does take multiple repetitions before you can do it strictly from memory. Thank you again for watching Fine Mathematics, our cafe calculations. I hope you enjoy this math calculation, and I hope to see you soon for our next videos. And remember, enjoy the process. And to become a patron for exclusive content only, please see the description box below.